Warning, the following IGDB insight contains super technical stuff. Viewer discretion advised.
We are here for a technical overview of IGDB.com, and this will be a technical presentation. But first, a little bit about me. I'm a bachelor in Skellefteå, and now I work as lead developer on IGDB.com. I learned Ruby on Rails at LTU, and I like the demo scene. I started liking it when I started developing games, and I'm a huge Zelda fan. And on my spare time, I like sojourning in the archipelago and growing strawberries. So about this talk, anyone can learn technology, but this will be technical. But don't be afraid to ask questions in the forum post and so on. And we might do some kind of video afterwards. And so this is me talking about technology and stuff. So we begin with some of the core technologies and services we use at IGDB.com, and then continue on with Uber optimizations I did, which was super awesome, therefore I want to talk about it. And if time, the future of IGDB technology. So this is the current technology stack, and I will go into details about these technologies in the upcoming slides. So the first one is JRuby 9000. It's only used in production. It's a JIT compiled Ruby, and why we use it instead of the official Ruby implementation is that it is JIT compiled, and it has full concurrency. It has full multi-threading. So we can leverage the computer power a lot better. Also, it is JIT compiled, and it has some advantages or disadvantages. And also, JRuby has also access to a lot of Java libraries, which official Ruby cannot have. But there are also some disadvantages with the JRuby, and that is, first we have to wait for the database adapters for Rails, for instance, and it has no support for C extension also. But those are the only disadvantages with JRuby. It's a very mature Ruby implementation, which is awesome because Ruby doesn't have a spec, it has only a reference implementation. And now we continue on to Rails. This is the Rails framework. It makes heavy use of Ruby metaprogramming, has a very large community, and a lot of large companies like GitHub, Heroku, Kickstarter, New Relic, Shopify, Indiegogo, and Netflix uses it. And it's used for the whole page. Everything is served from Rails except for the images. And we are trying to make a monolithic Rails application, just because it's simpler. Once you start to modularizing a lot, then it starts to get crowded with boundaries, and boundaries are very bad when you are trying to make agile programming. So therefore, we only use Rails as a monolithic application, even though we are planning on moving onto a more decentralized type of architecture further on. So this is Sidekick, and it is a very fast background worker. It uses Redis as a background queue, and it is multi-threaded. So we take full advantage of JRuby's multi-threading capabilities. Also, it's very easy to test, so you can test the background workers in a good manner. And now, this is Postgres. This is our main database. It's an SQL database, and it's a very reliable database. It's used everywhere. For instance, for storing users, companies, and games, and so on. It's a master database, so it needs a backup. And we have to go into the why it has grown on me. But it has grown on me, and you will see it in the Uber optimization part of this talk. And it's a very mature project. So it took a long time to get Upsert, for instance. And it what it lacks in tools, it makes up in reliability and performance instead. And why you should use Postgres is that if you need a lot of data that needs filtering, searching, and so on, then Postgres is a very good fit. And I know some some game developers might be in the audience, and then you can use SQLite for embedding it in games, and a lot of games is using it, like Total War and Civilization 5, and it's very common in tools and editors for games. And now we move on to Redis. Redis is our second main database, and it's not used for caching, but it's used as a very versatile key value store that complements Postgres very good. It needs backup because we are storing data, and that's why we don't use it for caching, because if the cache fills up the database, then we cannot insert new stuff into it, like for instance Sidekick jobs, and it is super fast because it's RAM only. So when you store something, it stores it in the RAM and then saves it in the background to the SSD on the server. And Redis. Redis is also very, very nice for storing perishable data, like small logs or authentication tokens, or counting API calls. It also implements the Google Hyperlog algorithm that can approximate unique sets of data in a very small space. Also, it has publisher subscriber, which makes it perfect for real-time applications like chat applications, anything WebSockets. I would totally use it for something like a game server or something, and synchronizing game data, so on. And also very handy expires function, so you don't have to expire a key, for instance. So that if you have let's say an invitation key, then it removes it automatically after a specified time, which it makes cleanup much easier. And this is Elasticsearch, and it's a document database with Lucene attached to it. Lucene is a very good string matching library. It has all the search functionalities, but the problem is that with Lucene, the document database, the database with Lucene is very hard to use, decentralized. So Elasticsearch builds up on Lucene and attaches a document database to it. And it also has search. We use it for search, autocomplete, and it has a very simple REST API to use. But it is a beast to master, and it doesn't need any backups because we are restoring every data, all the data from Redis and Postgres. So this is this is my tips for doing Elasticsearch, and my top tips is try to find a way to debug Elasticsearch, and then have try to see what token it creates and so on, and also don't try to make the string matching part perfect before you try to integrate stuff like ratings and release dates and so on. And I, to be honest, I have a little bit of a beef with Elasticsearch right now, because if you search for Zelda, you will see an abomination. So it is a lot of work to be done still, but now we have gone to a point where we are pretty satisfied. So on to the latest addition to our technology stack, and it is a NoSQL database. It's a graph database, Neo4j. A lot of companies use it, like Spotify, for instance, and it's used for recommended games. And the graph structure makes it very good for just recommended games. It has the simple REST API and also no backups, because they can be restored from Postgres and Redis. So yeah, on to Memcached, The sysmemcached is only used for mem caching, and if some logic other than caching is used, then use Redis for that. And cache hard, my recommendation is just make as much as possible on the fly and then cache it instead of trying to make any logic behind it. It's a quick RAM only database, and it is distributed and very fast. So it makes our pages load a lot faster, which you will see soon. So now on to services. I will go into details on these services, but these are the services we use. And we begin with the Godzilla, which is the Amazon S3, and in general it's file storage. We store all our files and backups, all our original images, and that's the only service we use from Amazon Web Services, because they are freaking huge, like Godzilla. And this is Cloudflare, and Cloudflare is how should I say, for the most part it is a content delivery network, but for me it's like they aren't completely respecting the HTTP headers we are sending away from the content delivery network. Also, it gives us free SSL and a simple firewall to configure. And also it has very good protection against bots and scripts and stuff. So, and also it has optimizations like compressing HTML, CSS and JavaScript, but we don't use those things, but they are very simple to use. And also the only bad part is that we don't have WebSockets support for it, which is a bit sad. So yeah, boom. So Cloudinary. Cloudinary is our image processing in the cloud. It processes all the images, so it creates thumbnails, WebPs, and the originals are stored in Amazon S3, and they are uploaded directly to Amazon S3, and then Cloudinary is pointed and downloading them from there. So we are using a library called Refile, which is created by Jonas Niklas from eLabs here in Gothenburg, and Cloudinary has a very nice GUI to generate derived images from existing images. Also, it provides us with their own content delivery network, which is always nice. You could also use it to create sprite sheets and so on. And also SendGrid. I don't know, I don't like email servers, so we use SendGrid. I recommend it wholeheartedly. It's a very nice email service, and it delivers very nicely. It has tracking for if an email has been opened, read, links were clicked, and so on. And a nice interface to see a reputation of spam filters and so use it. And this is New Relic. It's a performance monitoring tool, and it monitors the garbage collection time, the databases, and Ruby time. And you can also dig into the worst case scenarios that could happen, which is very good to see exactly what's happening there. But it has still average response time, which is a little bit bad. But it's hard to really do anything other than average, because some responses are very quick, like for instance autocomplete and so on, and they are also very many, and therefore average isn't that perfect to see. And the thing is that it's only me who knows how to use this in IGDB. And also we use GitHub. It's used for source control, for communicating issues, reviewing code, and also making it easier, generally easier to develop IGDB. And it's a very nice service. And last, we are using Heroku, and this is where our servers are hosted. It's very easy to develop, to deploy and monitoring, and so on. Very easy to get started. It is a premium service, and they do a lot of work for us, like making sure our servers are up and running. And the thing is that our server is currently served on a server with only 2.5 gigabytes of RAM, which is amazing. I'm impressed that it even works like that. Also, Yukihiro Matsumoto is here, works here, which is the creator of Ruby. So you are indirectly paying him to work on Ruby when you are using this service. So we got some questions here. Why we don't use DigitalOcean? I have to agree, they are very cheap, but you have to do all the wiring yourself, like the control panels, monitoring, backups, logging, and deployment, database migrations, and so on. And the thing is that the only person in the company that can do it, and I cannot be awake 24/7. That's physically impossible for a human, and we can also get a lot of Heroku dynos for the price of a sysadmin. That's required. So we are looking into Docker, and we have a project called Black Hole Sun, which is a project where we want to Dockerize everything. And also maybe move on to real hardware, and then have some redundancy in the cloud and so on. And also that would give us a lot of freedom to experiment. Experiment with interesting technologies like Varnish and Nginx and so on, that would otherwise be impossible in, for instance, Heroku. But there are problems with Docker, like persisting data, and might be some kind of flocker. We are looking into Docker Swarm, Kubernetes, and days as well. So this is a project much up in the sky right now, and we'll see where we go, but I believe that Docker is the future. So we'll see in the future how and where IDDB will be deployed. So Uber optimizations. I started on this is the use case. Response time. Okay, so now we move on to Uber optimizations. The thing is that the response times were suffering, and the dev team was super mad at me because of uncached database queries. And also the effect on the hardware upgrade wasn't that great. So here you can see that this is when we upgraded our hardware. This is how it was before, and this is when we upgraded hardware. And this is where we were when I had my Uber optimization in place, deployed. And it's a huge difference. We gained more from these kind of my optimization than from the hardware upgrade, which was super great. Basically free money. So I could have been like this. Oh my god, this is super fine. And the house is burning. But then you look at this. This is how Google classifies how fast the web page is. And we were here in 2000 milliseconds. So I could have been like this, that let's just wait on these guys to fix our performance problems. So the one in green is Tenderlove, also known as Aaron Patterson, which is part of Ruby and Rails core team, and he has made amazing performance optimizations for both Ruby and Rails. And the one drinking is Charles Nutter, which is part of JRuby core team and is the mind behind JRuby 9000. And they made a lot of performance optimizations for Ruby possible. And the one eating is Sean Griffin, which has been working a lot with Active Record and Rails and so on. But now he also works on something called Diesel, which we are very interested in using in the future. So let's fix this, because it wouldn't be an awesome presentation without fixing this. So we begin with the usual stuff, like finding the bottleneck. And the there was only one clear answer, the gigantic database query. Of course, it's always the gigantic database query. It took 50% of all the time spent in the database. So it was very good start. Good point to start with. So the reason was that it was this called it was related games column, and we were creating a Shakard index. If you want to know more about Shakard index, just Google it. But it basically calculates the union of the keywords and genres divided by the intersection of the keywords, themes, and genres. And this had to be done for every single game. And yeah, we could have done this in a background worker, but I prefer to do it as much as possible on the fly and not have that much duplicate data everywhere. So for the command case, we created Optimus Prime, and it's currently in place for games and companies. And initial experimentation was with a document database and storing games in something like CouchDB, but it wasn't good enough for me. And also, this is a cache, so it has synchronization issues there. And we could have used Elasticsearch as well. But it's much better to have it in RAM. So what we did was we created protocol buffers and stored those, Google protocol buffers, and store those inside Memcache. And that improved the command case a lot, because to get a full game page we only needed one memcached call, and we could also batch them together to form new lists of games and so on. Also, we used existing technologies so we don't bloat our application. But the problem was that it didn't improve the worst case. The worst case when all games were uncached. And also it created a lot of invalidation in the background. Like, for instance, if you change the name of a company, it invalidates all the games the company has made. So, why was it so slow? And you can see up here, it took about 1.2 seconds to execute. And the reason was that it had multiple selects inside a single query. So one row generated about 6 subqueries. And what did it do? It compared every game with each other. So one game compared with all the other games in the database. So that was why it was so slow. And then also it calculated all the themes and genres and keywords and so on. So let's try out. We tried out our new shiny toy. the latest one. Let's use Neo4j. And the reason was that I reused it recently, and a graph database seemed super logical for this kind of problem. The problem was that it wasn't. The result was 400% lower than the current solution. And that's why you have benchmarks. So, lucky we didn't use that solution at least. So, the problem with both those cases was that data is spread around. So it's hard to filter them out quickly. And it's hard to know what the next data is going to be. So the data isn't loaded into memory that quickly. It needs to get it from RAM and so on. So what's the fastest memory in the computer? And today it's the level 3 cache, which is here. And if you can cram into the processor's level 3 cache the data, then you are getting super fast. So lately I've seen a lot of code leveraging this, because a lot of processor has it. So that optimization works for a lot of different processors like ARM and PowerPC and x86 and so on. So we needed to change the data, how it was stored inside the computer, so we can fit it into this UC level 3 cache. So basically love your level 3 cache. The level 1 and 2 is much harder to control there. So therefore the level 3 is the best. So let's go low level instead. So this is fun. I like low level stuff. So Postgres has an int array column for storing 32-bit integers and a GIN index that's 3 times larger but 3 times faster lookup, just because it can index int arrays and so on. And we are only interested in filtering out the data, so only related games should be compared to each other. And so let's store everything into a 32-bit integer instead, or an int array. And so how do we store themes, keywords and genres in an int array? And the thing is that they have the same ID, but they don't need 32-bit to store every keyword, theme and genre in the database. So what we do is that we only use 28-bit to store the ID and use a 4-bit postfix. So themes has 4 zeros in the end, and genres has 001 in the end, and keywords has 0010 in the end. And in that way they are unique integers even though they have the same ID. And this is the database query afterwards, and that is much faster, as you can see here. And the reason why it's faster is because it can easily filter out a lot of data, and it can also filter, can also calculate it very quickly, because the data is just an array. It's a continuous stream of data, bits, which is easier to predict for the processor. So, other uses of this, integers. This seems like, oh, I just discovered integer data, but let's see here. Linux, for instance, they 64-bit Linux is only using 48 bits for pointers, for instance, and the rest of the 16 bits can be used to whatever they feel like. And for my personal game engine, I'm doing a sorting of my batching system with 64-bit integers. So the most significant bits is the shader ID, which is much harder to change than the model and the texture IDs. And I only use IDs to communicate with Lua, for instance, for my scripting and so on. Also tagging network communications. So integers move very easily through processors and the whole system itself without having to change that much. So the optimization resulted in about 7,000% performance improvement, and made yes, it made an extra database column plus some synchronization on top of that. But I think that was a fair trade-off, because the improvement was massive, and it also made me appreciate Postgres a lot more, and also made me realize that you could do a bit of low-level programming inside Ruby, because Ruby itself is an extremely high-level language. And this is the future of IGDB. We will continue use of Ruby. It will never be a rewrite from scratch situation. I feel that increments are the key to success. So what I will do first is defining a standard for microservices, so they can communicate in the same way throughout the whole application. And I'm thinking something like something basic, less bloat than, for instance, HTTP and so on. And also, I would love to do more experiments with Rust, Iron, and Diesel, which is amazing libraries, and it's very much more low level than Ruby. It's closer to even C++, which makes it very performant. It performs close to C performance. Also, some more experiments with Elixir and Phoenix would be super awesome. I feel that community has also grown onto me. So those are the future, possible future of IGDB. And also move to Docker. Docker as a deployment scheme. And the requirements are very easy. It should be as easy to deploy as Heroku on any kind of Linux machine. So we can have this automated fallback into the cloud and so on. Yeah, and that was the technical overview of IGDB, and I am hoping that people ask me questions about my technical decisions here on IGDB, and that would be awesome if I could have a new talk sometimes in the future.